I want to motivate linear functions again and see how we can turn some functions into a linear function if they're not already linear. So just as a reminder, here's some examples of linear functions. So here's a line that passes through the origin. I'm just going to call this f1 of x. Here's another example, f2 of x and f3 of x. So each of these, again, pass through the origin, and we can describe them generically as y sub n is some fn of x. So each y of n is some slope m times x. And again, it's important it passes through the origin here. And so you can go back to the definition of linearity and show that for each of these functions you can utilize superposition to recover y sub n from its various component parts. So what happens if we don't have a linear function, but we have a linear-ish function? So it looks like a linear function, except that it does not pass through the origin. So again, since the most important thing to be linear graphically is that it passes through the origin, we're going to try to figure out a way to make this function pass through the origin. So you might think, okay, let's just write down the mathematical equations. We have a y-intercept, y0. The x-intercept value is x0. And so we can actually write f4 of x as mx plus b, where m is the slope and b is the y-intercept. So this is the standard way we've been writing these equations for a line for years. So I'm going to write a slightly different function, f prime 4 of x is equal to f4 of x minus b. That is, I'm basically subtracting away the y-intercept, y0 in the graph. So again, this is not the derivative, this is just a different definition for some other function. So if I graph f prime 4 of x, it's a line that's just b units less than y. But this does give me a linear function, m plus. So let's look at a couple of points that have values in the original. So if we choose this point here, we get a value for y. That is, if we use this value for x, we get a value for y. If we use that same value in f prime 4 of x instead of f4 of x, then we're b units less. So we can pick a couple of different points and demonstrate this. If we evaluate f4 of x, we get this point, but f prime 4 of x, we get this point. So basically, for example, if this line was giving us the description for the force of a spring, then we wouldn't be getting enough force if we turn it into a linear function this way. That is, it would be telling us that it's using less force than it actually is. So let's see if we can actually write it in a slightly different way. So I'm just going to propose that we write f4 of x minus x0 equals m times x minus x0 plus b. So that is, instead of using the y-intercept, I want to shift everything over by the x-intercept x0. So now if we choose this point here, it's going to give us, if we offset by the value of x0, the same value for y. It's just moved it over by x units. So we're getting now the same force that we did before. We've just moved it over, basically. So we can show the same thing here for the squares. If we evaluate the function f4 at x minus x0 instead of at x, it's going to give us this value over here. So it's the same value, but on a function that passes through the origin. So the idea is that we've basically moved the axes over so that we get the same value for our function, but now we have a linear function instead of a function that has a non-zero y-intercept and a non-zero x-intercept. So if you remember, y sub 0, that's the y-intercept. We called that b in the equation. So now I can write the offset f4 of x minus x0 is m times x minus x0 plus y0. So I'm going to move the y0 over to the other side, and I'm going to quickly rename f4 of x minus x0 to just be some function f prime prime of x. So now I can write that f prime prime 4 of x minus the y-intercept is our slope times x minus x0. So this doesn't look like a breakthrough, but let's write this slightly differently. I want to imagine that this is just the difference in y is equal to some slope times the difference in x, or delta y is equal to m times delta x. So now we have a linear system. And if you choose delta y and delta x to be small enough values, then you could just rewrite them as another variable. And so, for example, you would get f equals m times t, or y equals m times x. So this is going to give us, essentially, a linear system.